and welcome to everybody. I hope I can be heard loud and clear all over the world, but we seem to have solved that, so let's get to work. As Fernando said, today's topic is the MST tool, and I hope that you will get an insight of what the possibilities of this tool are, and hopefully you can use it and share it in the future with your colleagues and so forth. So, first of all, the agenda for today is that I would like to, of course, introduce the tool just briefly, and then I will try to demonstrate the simple approach to the tool by a set of screenshots that I have provided to this PowerPoint. And I will show how we can calculate from, so to speak, the outside, the input power, the input side to the motor, to the application, and from the application and back to the input power afterwards. Then I will talk a little bit about what's going on inside in the engine room of the tool, to give you an insight of how we actually calculate the things. And then in the end we will wrap up the session with a live session where I want to show you, sharing my desktop, how the software actually works in a live situation, and fingers crossed that that will work as well. So let's see. And then finally, of course, we have Q&A, and yeah, that should be it. Okay. Firstly, myself, we heard Fernando. I think you mentioned most of it. I think I will add that I worked with ABB as a drive specialist for 5 years in the beginning of my engineering career, so I have a lot of practical experience with motors and drives. And also that I am the head of the accredited testing laboratories here in my company in Denmark for motors and pumps and circulators. So I have also tested a lot of motors and pumps and circulators myself. So I know what the feeling is about that, how it smells and stuff like that. And also, as the last point, I'm a member of the IEC Technical Committee Working Group 18, which these years tries to develop a standard, international standard on how to test and energy classify motors and drives as both drives as a component and motors and drive as a system, and that's quite interesting work as well. Yeah, the tool itself is basically invented as a result of a lot of projects regarding motor systems and system efficiency optimization that we have performed in Denmark since the late 90s. And this covers, for instance, systems optimization in general. It covers projects on permanent magnet motors. It covers projects on belt drives. We have had a project on gear motors, and we even had a project at some point regarding voltage control. Can we save energy by reducing voltage with, for instance, 10% and stuff like that? And all these projects seem to have a tendency to end up with a report standing on the shelf, and it was quite rare that anybody actually looked at this report. So at some point we decided to visualize some of our work in this context, and for this we invented the Motor Systems tool. So this is basically to be considered as the culmination of several publicly financed projects in Denmark since the late 90s. And then, of course, the key words for a tool like this, because we are well aware that we are not the only one having a tool, But the keywords for our tool should be that it should be very easy to use, it should be easy accessible. We hope for there would be no need for pre-knowledge. I'm not really sure if we succeeded in that, but we try to do it like that. But the most important thing is that we keep the tool completely impartial. And by that I mean that we have measured on many different brands of motors, many different brands of converters and pumps and fans here at our lab. And also I have received measurement results from other technical universities which have measured on systems with, again, other brands as well. So that we basically average these results so we don't favor any brands over others. So the tool is now and will always be in the future impartial in the calculation results. And the primary target group for the tool is basically engineers, machine builders, energy advisors, trainers at training facilities and stuff like that. It can also be used, of course, for policymakers and stuff like that to basically show what impact a certain level of minimum efficiency performance standard would make and so forth. So that's basically the thoughts behind the tool. The build-up of the tool is, I tried to illustrate in this slide here. And if we start from the left side, you firstly have to define the key components, which is the load, the type of load, the transmission, if any are present, and then of course the motor, maybe even with a drive if that's the case. After that, one has to put in a known duty point defined by power and speed. And this power and speed can be defined at the load or at the motor shaft or at the wall outlet. That's not really, it can be anywhere, but it's important to understand that all the calculations in the tool they origin from this one duty point and only one duty point. And this is to ensure that we don't have any iterations running far away in the calculations inside. So we have to stick, let's say, one finger in the ground, and that's the duty point. So input key components and the duty point, and then you go to the main screen window in which you can have dynamic calculations. They can be automatic or manual, and then you get the results directly. So pretty easy to come to the result. From the main window, we have different other calculations, but we'll see them as we move on. So let's start with the screenshots of the tool. The first screen you meet when you start the tool is an introduction screen, and then you see a screen looking like this. And this is basically a grayed out version of the three key components, the load, the transmission, and the motor and the drive. It's grayed out now because nothing has been selected. And the user can now select in any order the three key components. In this example, I start by choosing the load profile, and here you can select between 4 standardized profile of motor systems. And in this case, I choose the latter one, which is a pump and fan, where you have a squared relation between torque and speed. Well known to many of the listeners here, I'm sure. On the transmission side, if you push that button, you can select that there's no transmission. You can select that there's a gear transmission. In the gear section, we have, for now, 3 different types. We have the worm, the helical, and the bevel gear. I'll get into that later. And you can also select transmission of belts, and there we have numerous belt types. And within the specific belt type, you have, again, variants and so forth, and you have to input a lot of different parameters. which you have to input, and therefore making the tool maybe not that easy to input as we hope for. But yeah, that's a consequence of the complexity of the system. Anyhow, we now selected the load and the transmission, and then of course we have to select the motor. And the first splash screen appearing when you push that button is this one, where we can select a standard motor and drive or a PM motor. I will not go into PM technology today, but it will. It is an option selectable. In this case, we have no nominal data for the motor. They are all 0 to the beginning, in the beginning. So if that's the case, you don't know the nominal values of your motor, you can push the button called standard motor, the one down here. And if you do that, you get another splash screen where you can select a standardized motor. In this case, the example is a 15 kilowatt IE3 motor. And by definition from the IEC standard called 60034-30-1, the nominal efficiency of a 15 kilowatt IE3 motor has to be 92.1. And that's basically the number that will be used for the calculation if this motor is selected. In this, my very first example, I actually put in some motor values, just an example. It's a 4 kilowatt motor, 380 volts and so forth. And the program calculates the nominal torque and the nominal efficiency of the selected motor. And if I input this, it looks like this, and I get a green light that I have valid values in my motor selection. And after that, I have to select if the motor is direct online. It can also be soft starter connected, or it can be connected by a frequency converter. The frequency converter model as today is either a constant flux model or an automatic energy optimization model. This is basically, I think in most frequency converters today is selectable to either have standard flux or energy optimized mode, even on the cheaper brands. After the selection of a motor, and I selected to be direct online in this case, I have to put in the known duty point. And the known duty point in this case, as an example, is that I have measured, let me see, where's my mouse, it's here. I have measured 3.6 kilowatts at the wall outlet. I have read on the nameplate of the motor that it's running 1415, so that's my guess, my best guess. And then I have to point at this point here to tell the program that I'm now calculating in the P1 as opposed to the others. So that's my known duty point for now. And then I come to the main screen of the MST tool. And what you see in the screen here, if we start at the right side, that is that I have a black number here, P1 input power 3.60, and that's black because that's what we entered manually. We also see we have an estimated cost for an entire year running of that. We have now here the price in euros. That can be changed by pushing the money stack here if you have another currency. We also have a calculator here basically telling the user that the calculation master of the program right now is P1. So everything is calculated from this point. And that would mean in this case that we now calculate toward the left to see what we have in the other end. In this case, our calculated efficiency based on the input power in this motor would be 78.1. And if that's the case, then it's easy to calculate the shaft power, which would be 2.81. We already input 1415 as the speed, meaning that we can easily calculate the torque in this duty point. So that's the three values. since we don't have any transmission, this transmission efficiency is grayed out and has the value 100. And then that basically means that we input to our load, in this case a fan, the same values as before. For starters, the program just defaults with a automated ETA calc. It's right now locked on 65%, and that's just the default value. It comes from absolutely no real life thing. It's just a number to get us started. But in this example, I have actually been out measuring on the fan. That means that I can actually push this button down here. I have a known duty point. If I push that button, I get a splash screen looking like this. In this case, I select the fan. The equation for fan, standard equation, looks like this. And if I have the, in this case, I have to put in 11,000 cubic meters per hour and the pressure 500 Pascal. That would calculate to 1.53 kilowatts of hydraulic power. And if that's the case, because I have 2.81 coming in, then the efficiency of the fan must be 54.32 at this speed. So that basically means that now we see a change over here, and we now have the entire chain of the entire motor system telling us the efficiencies of all the components included. Of real-life measurements, we only had the electrical power input, and then we had the hydraulic output in terms of pressure drop and flow on the fan. And then we have all this information. So now, if I want to see what is basically happening if I change the motor to a better motor, because this was an old motor, then the correct approach using this tool would be to switch the calculation master to P4. So now the gray, it's no longer black here, it's gray, and now it's black in the P4 section, and the calculator as well have moved with it. You do the actual selection down on the button here. And I do this now because I want to have the same performance on the fan, but now I will have another motor. So basically what I do now is that I push the button over here, this button, change motor and drive. When I push this, I see a splash screen. This is now I have selected basically using the blue button here. I have selected an IE1 motor, 4 kilowatt IE1 motor, and here we can see that from the same IEC standard, the efficiency should be 83.1 of an IE1 motor. And then if I insert that, the system automatically calculates in going to the right, from left to right in this case. And we have the 2.81 shaft power as before, but now we have a better efficiency on the motor, meaning that we have less input power, 3.44. Before it was 3.60. So now we have an annual cost which is less than before using an IE1 motor. The problem now is that IE1 motor is no longer allowed in Europe and in the USA and many places in the world. So quickly we instead select an IE2 motor. Again, we see the efficiency of the IE2 is higher. Before it was 83, now it's 86. I select the the IE2, and then I keep the calculation from left to right, and now I only have 3.29 of input power to this system. And the cost is now 5,180 euros. Before, in the beginning, I think it was 5,680. So this changing of motor will give me an annual saving of approximately 500 euros. So that's basically how you can go into the system from right to left and go back from left to right, changing the motor. If you look at the top I just go back, if you look at the top of the screen, I move this one here. You can select the before situation, and we can select an after situation, where we can put in duty points, then energy calculation. But I will demonstrate that in a short while live. I think I will go to the inside of the tool now. When calculating motors, we used as a starting point the classic shape of a asynchronous motors, looking like this. For all sizes of motors, it has a different bend and so forth. But basically, it looks a bit like this. Normally, you see that the nominal duty point, basically always read from the nameplate. It would be something like this. And normally, the efficiency of the motor is a little bit higher at 75 and looking like a nominal at 50% load. And that's quite normal for asynchronous motors. And for this, we basically, as input to this equation, only need output power nominal and efficiency nominal. And then for the calculation, we just need the power if it's input or output, because the speed is given on an asynchronous, not connected to frequency converter. And speaking of that, the model inside is basically based on a study from Aalborg University in Denmark from 2000. A PhD study where a guy called Abrahamsen was investigating, calculating on energy optimized drives in certain sizes and stuff like that, different speeds. And again, the input parameters for this is the nominal output power, the nominal efficiency of the drive and the motor. And for calculating, we just need the speed, the torque, and of course the way we control the drive. Is it energy optimized or is it not? So that's basically the inputs for the drive model. And then again, we got a lot of measurements from ourselves and from other guys, universities and stuff like that. And that basically meant that we, in the end, used these measurements to make a model, an equation, as we see it down here. It's in Danish, but if I translate it a little bit, the input parameters to this equation is basically the nominal values of the components here. It could be input power and output power. That means the nominal losses. And then we need the nominal torque and the nominal speed. And from this, we can actually calculate the efficiency in any given duty point by knowing the torque and the speed. This can be done on both direct online motors, on motors connected with VSD, on standard clocks, on automatic energy optimization, and also on permanent magnet motors. So inside, we now basically have this equation, but we change the constants in front of the different, depending on which system that we are calculating on. And this has been verified with a lot of measurements, and it's not that bad, actually. So that's how we calculate the drives. We calculate the gears from an early project in Denmark. We looked at worm gears, bevel gears, and helical gears. And here we see some small graphs of the efficiencies in terms of speed and load. We have turned them into, make things simple, we have turned them into a plane in space, where you basically have an inclination of the partial load, you have an inclination of the partial speed, you have the nominal efficiency of the gear, and then you have a constant depending on if it's a helical gear or it's a worm gear or whatever. And these things the user has to input here, and this is basically where the program is not that simple anymore. But we realized at one point that if you have to include a gear in the calculation, things are not simple. But we have tried to do it as simple as possible. The same thing goes for the belt drives. Here you see some graphs of belt drives. We have performed tests in the past. and from each type of belt drive we have a set of equations which is completely unreadable at this point. But what you can see is when you input to belt drives, in the motor systems tool you have to select, in this case, a classic V-belt which is cocked, and you have to select the type, and you have to select the ratio, and blah, blah, blah. And then, of course, you have to select where is the smaller pulley placed. Are you gearing up or are you gearing down? That's also quite important in the calculation. So again, not simple, but with as few parameters as input as possible. And the way we actually calculate using all these models I just shown are that we basically, normally we know that we have a formula where we go from P2 to P1. That's normally a very known formula. And what I basically do inside the tool is that I calculate from P2 to P1 1,300 times from 0 to 130% load. I put that in the table with the relevant input-output relation in all these loads. And then I can do a simple table lookup to find the input power to give me the correct power on the shaft. So that's, instead of doing actual iterations online, we basically do a table when we have a new product. We make a table and then we put it in and it's calculated once and then it's table lookup. And that's really a simple way to do it and it's actually functioning. And this goes for motors, it goes for belts and gears and frequency converters and you name it. On the application side, you saw before that you can put in for fans the equation here. We also have a section for pumps. On the fan side, we only have flow and differential pressure. On the pumps, you can also input the viscosity, the density and the gravity, of course, when we talk pumps. And then, of course, flow and head, and then it can calculate in the same way. And you can also actually choose what we call other motor duty. We don't really have an equation there, but you have two parameters linking to 1 kilowatt power. And this could be maybe what should we say, luggage carrier in the airport, then maybe the speed and whatever the weight or something like that. And then you can get some suggestions of efficiency on different machines, which right now is in Danish, but we will translate very soon. So, okay, and then a very good thing here is you can put, if you actually have a curve, you can actually put in the full profile. This is a ventilation curve or fan curve. And you can see I have 12 red dots on this curve. These dots I basically have put into this scheme. And when I do that, I can actually, let me see the mouse. I can basically get an automatic calculation from the curve. So if I input the 12 duty points in the table, I can calculate efficiency and speed from this. And in this case, I have 30,000 cubic meters per hour. That's the same as 8.3 cubic meters per second. So if I go into the graph, you see I have 10 here, so 8 must be here, so 8.3 would be here, and then I have 500 Pascal. So this is basically the duty point calculated by the program. And if you look at the speed curve, which is 1,000 here, and the calculation is 1,019, so that's not too bad. And the efficiency, we have here we have 70, and here we have 80, so this point would be something like 72, and that seems to be very good. So that's another possibility. Automatic calculation of based on input curve. And then, of course, we have energy calculation on the system. And I think I will show that live because I can see time is now running. But yeah, I think that wraps up the inside of the tool, how it's calculated, and the way to go from both sides. So now, Fernando, if you would give me the screen, I will try to move into the sharing of the screen and see if that would work. I hope so. It should work. Yes. Here we have the screen, and I have already started the tool, as you can see. I will start to say, I show you here the Motor Systems org, the web page of the 4E EMSA. This is the address. If you, this is the main page, and if you push here, you can see the Motor Systems tool. Hopefully you have already downloaded the tool by now. But what you can also download is the calculation examples here, and the latter one, we have an exercise and also the solution, and it's free for download, and you can use that to exercise the tool, and of course also the first exercise. I will use the second exercise today, and for this purpose I have prepared here. This is basically the solution to the exercise, and this is the graph, following the exercise. And now I will quickly run through the first part of the exercise. It says in the text, you're an energy advisor, and you know we have a fan installation, we have a fan directly coupled to the motor, and you are on site and you can read the nameplate. And we have here 50 hertz, 5.5 kilowatts, 380, 12 amps, and so forth. So that means that I have a fan, so I select a fan. On the transmission side, I have no transmission. And then the motor and drive side, I have to put in the motor data we just saw there. So that would be 5.5 kilowatts, 380. We have 12 amps. We have 0.83. And we have 1425 RPMs. So here I put in the manual nameplate of the motor. I say OK. In this case, it's not soft starter, it's not frequency converter, but it's direct online. So OK to that. And then the known duty point, if I go back to the exercise, it says here, you find the power consumption of the installation to be 6.15 kilowatts. And this is measured at the wall outlet, so that would be at the P1. We have 6.15 kilowatts, and I say OK. So this is basically my duty point for this. So you recognize the 6.15 kilowatts from the wall. The calculation master is here. We have a suggested efficiency of the motor 83. So that means that right now I'm delivering 5.12 on the axis, on the shaft. No transmission. So the input to the fan is 5.12 kilowatt. And it's a 4-pole machine, given it's 1425. So if I look at the fan curve, I have to look down here. I don't know if you can see my mouse. You can probably not see my mouse, but I'm on the bottom part of the power here. You have a 4-pole machine, and if you look at the power input, 5.12 is basically on the red line here called number 2. That would be 5.12 input power to the fan. So if we input 5.12, if this is our duty point, then we can, going up, we can see that the flow of the fan is very close to 4 cubic meters per second. And if we go even further up, we can see when we touch the curve for the 4-pole machine of this fan and go out to the left, that we have something like 1,000 Pascal as the differential pressure on the fan right now. and the other here is basically converting cubic meters per second into cubic meters per hour, because that's what I calculate in the tool. So if I basically put those two parameters into my tool here on the fan, now it's flashing because it's 0, that's not a valid value. In this case I have 14,400 cubic meters and I have 1,000 Pascal. Then I get, because I know that the 5.12 is the shaft power delivered by the motor, I know the speed, and then if the hydraulic power is 4 kilowatt, which it is, then the efficiency must be 78.11. So that basically gives me the entire picture of this duty point here, going from 6.15 to a delivered 4 kilowatt hydraulic power of the fan in this case. And this was basically the question of the first exercise. You have to estimate the flow, which is 4 cubic meters per second and 1,000 Pascal in this case. The next part of the exercise is basically the same. We have to do it 4 times because we want to calculate the power consumption in 4 different duty points. And the way you do that is basically in the before table, you have a duty point here with all the measured values. You can add the line by using this button here. When you push that, you are asked to input the number of running hours per year in this duty point. And if we look at the exercise, that's in this case 1,800 hours per year actually for this duty point. So I put that in here. And then this line up here is basically copying all the values from below into a scheme, and on the right side it actually calculates the kilowatt hours per year. This has to be done for 4 duty points in this exercise, and I have done this already just to save time for today. And here you can see the 4 duty points. You can hopefully recognize the input power. 5.4 is here, 6.15 is here, 5.82 is here, and 5.34 is here. And the running hours each year, and then the kilowatt hours and so forth. And basically, the exercise here asks what is the annual power consumption in this situation, and now I have inputted, and if I go to energy calculation, it basically summarizes the number to 37,586 kilowatt hours per year, which is the answer to that. The next thing is, what happens if we change the current motor to motor of IE2 level, which is legislation in Europe. And that basically means that you have to input the same duty points on the motor shaft. So you have the same hydraulic conditions, but you have another thing rotating the motor shaft. I actually already did that with an IE2 motor, just to save time. And here you recognize, if you see the before table, these are the numbers of the motor shaft kilowatts. And if I go to the after table, these should be the same. So I keep the motor shaft steady, only changing the efficiency of the motor and thereby the efficiency of the motor. And if I do that, input them like I did here, so I have now a before situation and I have an after situation. Then when I push the energy calculation tab, I see difference in when changing to an IE2 motor. You also see a visual presentation. The difference between the red and the green is of course the savings, and the numbers are on the lower right side. in this case, the savings is 1,544 kilowatt hours going to IE2. If I do the same exercise with an IE3 motor and go to energy calculation, the savings are, of course, higher. The before situation is the same, of course, but the after has less kilowatt hours if we go to IE3. And that's basically the answer to that question. Yeah. In the second part of the exercise, I include belt drive, and I include how to optimize on a belt drive. I don't have time to go through that today, but I strongly suggest that you do it yourself. You have the solution with the correct numbers here, so it should be doable. And my best advice would be to look at the solution on the graph and the curves, and then you can basically, hopefully you can follow the ideas behind that. Yeah, I think that's what I have time for in the live thing. And now I stop sharing, and then Van will give me back PowerPoint. Yes, thank you very much. And the last thing I want to say is, in terms of what is the future of the tool, I would say that we have already arranged to translate into more languages. It will probably be done this year to German, and hopefully in the future, if we find the resources, we can do even more languages, which would, of course, extend the users, the users of the tool. What I would like to have, which I don't have right now, is a slip calculation of the standard motors inside the tool. It shouldn't be a big problem to include the change of speed, because right now the speed is fixed unless you change it, and of course this has that's not really the case in real life. When going to an IE3 motor, typically will run a bit faster than the old motor. And then we would like to include new technology motors. We have permanent magnet motors by now. We have, I also have, in cooperation with University of Ghent in Belgium, we will soon include the synchronous reluctance drives as well. We would like to improve of the application calculator. We would like to include, for instance, compressors and hydraulics. And we would like very much to include the energy calculator side, possibility to print out, to save, and so forth. And also we would like to include legislation values for different components. In the European side, we have the eco-design, the minimum efficiency performance standard. It could be very easily be included, and the same, of course, goes for all other parts of the world. US, China, whatever. And then last but not least, during my work in the IEC standardization, I think in the future I would be able to include some of the standard losses, the model for losses in the standards, in the IEC standards. If they could be included in the MST tool, that would be a strong add-on, I think. So that's some of the plans, at least. And yeah, I think that wraps it up. My contact information you can see here. I work in Denmark in Danish Technological Institute, but I also am a part of the 4E EMSA. I showed you the web page, and the address is here, and I strongly hope that you will use us. We have a lot of valid information, and of course sign up for the newsletter and download the tool and